Okay, so in the third lecture, we're going to continue our discussion on linear regression. So let's remind ourselves what the problem is. So again, we have as data measured pairs, x, y, where x is the input, and we'll assume that's in dimension rd plus 1. The plus 1 because we take each input x and we attach a 1 to the first dimension of it, so we extend it by 1 dimension for the offset. And the output y is in R. And so we're predicting a real valued output, which is what makes it a regression problem. So the goal is, again, to find a function f that takes the input x and maps it to the output y. So we're taking an input in rd plus 1, and we're mapping it to an output in R. And we're doing it in a way where we can approximate y well by this function f, where we input the corresponding x, and also a weight vector w, which is the parameters that we're going to be able to change or modify in order to change the function and change how it maps the input to the output. And again, the definition of linear regression is that the function f is a linear function of the unknown parameters w. So we saw last time that this doesn't actually mean that we have a linear function of the inputs x. We could perform some nonlinear function of the inputs x and then send that to f. And as long as it's linear in w, we still would have linear regression, and the solution for w is solved by exactly the same equation. So let's continue our discussion on least squares. So again, to review, the least squares objective function finds the value of w that minimizes the sum of squared errors. So what we have is the output yi is approximated as a dot product between the input x and the coefficient vector w in the simplest case. Last time we saw how this could actually be a nonlinear function of x, but for notation, let's just talk about vector x. And we take this error, square it, and sum it up over all of the data points that we have. We can write this in a nicer matrix vector notation by taking these vectors x, I, and putting them along the rows of a matrix x, capital X. So this matrix is n by d plus 1. And then we take the vector y formed by taking each of these outputs, y1 through yn, and constructing a vector out of them. And then we take the error vector. We have the error vector, which is the point vector y minus its approximation, xw. This is the vector of errors for all n of our data points. And when we take the dot product of that error vector with itself, we're summing the square of those errors. So taking this objective function L, finding the vector w that minimizes it, because we're seeking to minimize the squared sum of squared errors. So we take the gradient of L with respect to the vector w. We get this solution as its gradient, and then because we want to find the minimum, we find the vector w at which the gradient is equal to 0. So we find the point w at which this function is minimized. Another way of saying this is find the vector w at which the gradient of this function is equal to 0. We solve and we get the least squares solution, which is equal to this.